Welcome guys to lecture number 5 in Introduction to Cosmology. So in the previous section we had covered about the cosmic dynamics, and so in this lecture we'll cover more about the single component universe. So basically we have seen there are many components as to you have matter, you have radiation, you have stuff with different energy densities, you have cosmological constant, you have the scale factor, you have various other components that through which we can understand the universe better. So we'll cover more about that in this lecture to start off. So as you remember, what we have learned from the previous lectures, this is the equation number 1 tells us the general Friedman equation using the concept of general relativity. And the second equation is the fluid equation, and the third equation is the equation of state. So this equation we'll be basing off our the topics that we're going to cover based on these three essential and very important equations in cosmology. So the first one we're going to do about is the energy density. So as we know, this is also a very important aspect to the a property, basically a property of the universe. So we know that matter, as we have seen in the previous lecture, has the equation of state constant omega that is equal to 0, and radiation has equation of state equation of state factor omega to be 1 by 3. So, and we will also include the cosmological constant in it, which has the equation of state parameter to be -1. So we know that the universe around us consists of matter, which is both relativistic and non-relativistic. So we have electromagnetic waves, and we have photons, which is relativistic, and we also have, say, our Earth and other heavy huge mass particles that are not relativistic. So we have all both these two components, and we also have a cosmological constant that we have seen in the previous talk, like how it is basically the expansion which causes the expansion of the universe. So so first thing is that the one thing to cover, one way to cover all these three components in one in our using our equations is that like fortunately for our simplicity, these the pressure all the pressure for all the pressure and energy density equations, the components for different equation of state parameter just add up. So for non-relativistic matter and for relativistic and for cosmological constant, the equation of state parameter just adds up for pressure and energy density equations. So equation number 4 just tells us that we can sum over all these components for the total energy density of the universe, that is sigma omega for all omega, given by e in sigma omega. So for each parameter, you can just sum up each component. You can just sum up and get the total energy density of the universe. So the total pressure, as I told you before, it also behaves in the same way, wherein you can just individually add up the equation of state variable for individual components. So your total pressure can be given as the sum of all the individual components' pressure. So that is where what we have seen in the previous lecture, that is the pressure can be given by the equation of state parameter times the energy density. So because the energy density and pressure add in this way, the fluid equation that we have seen that is equation number 2 can be written in as equation number 6. So that is epsilon omega dot plus 3a dot by a times epsilon omega plus p omega is equal to 0. And so this can be also written, since after we substitute for pressure, that is omega times epsilon omega. So we can write we get the equation simplified mode, equation number 7. So after we write the dots in terms of the differential symbols, so we can have d epsilon omega by omega is equals to -3 into 1 plus omega dA by a. So since we know we are considering the omega to be constant here, so if you have for a constant omega, we can integrate and we can find the value, that is epsilon omega of a is equals to, this is actually the a here is the scale factor, so is equals to epsilon omega comma 0, which is basically the energy density of a particular component at the present moment, times a power minus 3 into 1 plus omega. So with equation number 9, we can conclude that the energy density Em for non-relativistic matter decreases as the universe expands, because see, we can see that since E epsilon of omega comma 0 is at the present moment, we can normalize it, and for epsilon, so we can say that epsilon omega of A is directly proportional to A to the power minus 3 into 1 plus omega. So it is basically inversely proportional to the cube of the scale factor. So as you can see in equation number 10. So for non-relativistic matter, for which you have omega to be 0, if we substitute in equation number 9, we get equation number 10. So what we can say is the energy density for the non-relativistic matter decreases by a factor of 1 by a cube as time increases or as universe expands. So this is a representation of how, as time progresses, how the relativistic and non-relativistic matter, kind of the energy density is kind of decrease as the particles go apart from each other as the universe expands. So but we can see that in equation number 11, which is given, we can see that the energy density in radiation drops more at a more faster rate. That is, so from equation number 11 we can see it drops it by a factor of a to the power 4 as time increases. So why is it so? Why should there be a difference in the the rate of the rate of decrement that is seen in the energy density as time progresses? So for this we can express this phenomena by considering the fact that as we have seen in the previous equation, that n to the that the number density or the energy density as such is directly proportional to the a to the power minus 3. But as universe expands, the particles are also neither created nor destroyed. Right? So that's what we have seen. Energy, basically, the law of conservation of energy states that the particles can neither be created nor destroyed. So since we're considering the relativistic matter here, so we also have the fact that the energy can also be of a relativistic particle can also be expressed by the equation E is equals to hc by lambda hc by lambda. So which is, in this we can see, so even though we have seen in the previous segments that lambda is also inversely proportional to the scale factor. So we also include this parameter. So we can say that the energy density for a relativistic particle is directly proportional to the the alpha to the power minus 3 times alpha to the power minus 1 also. That is due to the E is equals to hc by lambda equation. So equation number 13. So we can justify that the radiation or the energy density of relativistic particles drop down by a factor of a to the power minus 4 as time progresses or as universe expands. So from what we have seen before, the cosmic microwave background, so we see that it is basically a relic of time, because it has always been existing ever since the universe started to expand, started to become transparent, allowing the photons to travel through the universe and not reflecting it from being in its opaque state. So this is what we have seen in the cosmic microwave background. But if we go further back in time, we also reach at a point in the universe, for the point after the Big Bang, the given theory of Big Bang happened. So we can also try to do experience the same. I mean, explain the same thing that that could have happened in the case of neutrinos. So basically, at a point where where the universe was hot and dense, it was dense enough to be opaque to the neutrinos as well as it was dense to the photons. So as a consequence, there should also be a cosmic microwave neutrino background today, which is also similar to the cosmic microwave background. So we also expect the energy density, and the number density of the neutrinos to be comparable, but cannot be exactly equal to the the energy density and number density of photons in the cosmic microwave background. So after doing a detailed calculation, we can try to explain we can try to find the expression to give quite accurate value for the energy density of each neutrino flare. As we know, as I've told in my previous lectures, that neutrinos are of three flavors. There's electron, that is mu neutrino, and then you have tau neutrino. So for each flavor of neutron should be for the epsilon, as the energy density is nothing but 7 by 8 times 4 by 11 to the power 4 by 3. That is basically, oh, I am sorry, this is for CNB. Sorry, this is CNB. So this is sorry, CMB itself. So this is approximately equal to 0.227 times the energy density for the cosmic microwave background. So basically, what it says that the energy density of the cosmic neutrino background should almost be equal to 0.227 times the energy density of the cosmic microwave background. And the density parameter of the cosmic neutrino background, considering all the three flavors of the neutrino, should be omega of V should be mu is equals to 0.61 times the omega of the density parameter of the cosmic microwave background. This is the after doing some observation and coming up with equations for neutrinos as which is in comparison with the cosmic the relations for the cosmic microwave background. We come up with the following expressions in terms of the cosmic microwave background as we are comparing the energy densities and the number densities with the cosmic microwave background. And the mean energy per neutrino will be not exactly equal to, but somewhat similar to the mean energy of photon. So you have mean energy of neutrino to be 5 into 10 to the power minus 4 divided by A electron volts. So if all neutrinos species are effectively massless today, so we can, since we have not yet detected, like we cannot say for sure, but we can say that they have very little mass, but it is very minute, and that's what we have been able to observe with our current technology as such. So if we consider the neutrino species to be effectively massless today, so with mc square, that is the Einstein's E is equal to mc square equation. So m nu for the mass of the neutrino to be very less than 5 into 10 to the power minus 4, then the present day density parameter in the radiation should be what? So basically, we have the cosmic microwave background and the cosmic neutrino background that are associated that are present in the universe. So for the density parameter in radiation as such would be the sum of both these, right? So you have the density parameter of the cosmic microwave background at the present moment, the comma 0 indicates at the present moment, plus the density parameter of neutrino at the present moment is sum of these two, and then you get 8.4 into 10 to the power minus 5. So to to effectively gather a more greater picture by understanding the cosmic neutrino background, which is also associated with the cosmic microwave background. So we describe a model of the universe, which is called as the benchmark model, like how you have benchmarks for different categories in various fields. So you have a benchmark model for the universe, wherein you can say at the ideal part of the like what we expect it to be. So it should be the density parameter in radiation should be exactly equal to 8.4 into the power minus 5, and the density parameter in radiation should be zero point 0.3. Sorry, for non-relativistic matter to be 0.3, and for and for lambda to be 1 minus the density parameter for radiation minus the density parameter for the non-relativistic matter. So we get the density parameter for the cosmological constant at the present moment to be approximately equal to 0.7. So this is in a benchmark model. This is but we know that for a fact that we still haven't discovered the presence of cosmic neutrino background as such. But if it so exists, or if it so is pertaining in the universe as we expect it to, the benchmark model comes into play, and we expect these values to be these values to be justified with the given relations. So this is an idea about the cosmic neutrino background which is present in the universe. So in the benchmark model, at the present moment, the ratio of energy density in the cosmological constant to the energy density in matter is basically the ratio of those two. So you have that to be equals to the energy density at the present moment divided by energy density of the the non-relativistic matter to the power a cube. So a is the scale factor. So the moment matter. So since we know the universe, started to expand from a single point. That's we are considering the Big Bang theory here in this case. So at one point in the timeline of the universe, the expansion constant, basically the cosmological constant, should have been equal to the energy density of the cosmological constant should have been equal to the energy density of the non-relativistic matter, or relativistic and non-relativistic matter. So we are trying to find at what point it should have been, or what or for what value of the scale factor should it have been equal. So this we can try to understand from equation number 19. So the scale factor at which the energy density of cosmological constant and the energy density of matter would have been equal is at 0.75. And for reference, the present scale factor is always normalized, so we take it to be 1. So at a scale factor of 0.75, that is obviously way past, since we know that our current universe is dominated by the cosmological constant, so this should have happened in the past, right? So at a scale factor of 0.75, the energy density of cosmological constant and energy density of matter was equal. So we try to find using the same using the instead of cosmological constant, we want to find the equivalent point for both matter and radiation in this case. So you have the relation given in equation number 20. So we can see that it is just basically directly proportional to the scale factor, the ratio. So we calculate using the given using the present values of the energy densities in both non-relativistic matter and radiation, and the current value of scale factor. We can also try to get the point or the value of scale factor at which the radiation matter equivalence was present. There was the energy densities of radiation and matter was exactly equal. So it was at a scale factor of 2.8 into 10 to the power minus 4. So in a universe that is continuously expanding, scale factor A, as we have seen in equation number 20, is monotonically increasing as a function of time that we have known, right? Since scale factor is only dependent on time. So in this benchmark model, we consider this also. So thus, in a continuously expanding universe, the scale factor A can be used in the place of cosmic time t. So we also try to represent the moments or the kind of time and distance in terms of the redshifts, right? Because it is way more easier in to get the values in terms of redshift, because we are able to observe it directly, and we can also instead of using a cosmic time, we can use the transmissions the transformation from the scale factor to the redshifts. So it is much more easier in that sense. So we know from previous parts wherein you have the scale factor to be 1 by 1 plus z. So if you put in the values from equation number 21, so we try to express the kind of at a specific point or a specific time in the universe. So we use the value of redshifts because it is way more easier to represent it in that way. So you can say that at a redshift value of 3600, we can the point at which at the redshift value of 3600, the energy density of matter and the energy density of radiation was equal. So you can try to express events in the universe based on the values of the redshift and the scale factor at that moment. So this is about the the energy density and universe with energy density as such, and no curvature or anything else. It's just about the energy density. So this is one component of the universe that we have seen. So for a given energy density, so we include the state parameters. But one thing to note in equation number 23 is that each value in the right hand side has a different dependence with the scale factor. So we see that for energy, it is directly proportional to a square, as you see, and then for matter, it is directly proportional to a cube, and then for cosmological constant, it is directly proportional to a. So each point in the for each value in the right hand side, its dependence with the scale factor is different. So that is one point to note in this. So we can easily try to substitute the values and get a precise value of all the observables that we can use for this. So this is about the energy density. I mean the energy density component of the universe. So let's go to the second condition, that is the curvature. So we know curvature is also like a very essential thing to that is required to understand the nature of the universe, since our universe is also curved. So we consider at a point where we consider only the curvature to be there, and no energy density or no what is it, cosmological constant in this case. So we just consider a curved expanding universe. That's it. So an empty, static, and spatially flat universe in the case that the k in this equation number 24 that we have derived from the Fredman equation. So in this case, we are taking the k value to be 0 and a dot to be equal to 0. So this is also one of the solutions of the Fredman equation. So it is permissible, right? Because it can happen, because we are considering that our universe that it works under the the Fredman equation. So we consider one of the solutions of the Fredman equation to where k is equal to 0 and a dot equal to 0. So this is an empty, static, and a spatially flat universe. Since k is equal to 0, that means it's a flat or a Euclidean space. So since it's a flat or Euclidean space, the geometry that can be used to describe the universe is given by the Minkowski metric. So we can use the laws of special relativity to kind of understand the universe, that specific universe. So uh, we can see that in the equation number 24, if we substitute the value of k to be 1, that means it is we are taking the case of a positively curved universe. So if we take the value of k to be 1, then we get the value of a to be an imaginary value, right? So a scale factor cannot be imaginary. So according to this, your positively curved universes are not applicable. So you only the if the value of k value of k can be taken to be -1, so that the scale factor is a real number, so it exists. So we can also consider a negatively curved empty universe. So this specific type of the universe or specific component of the universe is called as the Milne universe, Milne. So it's called the Milne model of the universe. So this is one thing to note. So you can go and search up a bit more on the website about Milne's universe. You have very exciting stuff going on there. So if for a negatively curved expanding universe, so you have the given equation to be a dot square is equals to plus or minus c by r naught, since that k value is taken to be +1. Sorry, -1. My bad. Sorry. So in an expanding universe, in the integration of the equation 25 can lead us to the equation number 26, that is a of t is equals to t by t naught, where t naught is equals to r naught by c. So if we consider, so from this, what can we expect from the negatively curved, negatively curved spatially flat universe? So what can we in a negatively curved universe? What can we expect? Excuse me. So if we consider this part to be in a Newtonian sense, so we can say that there is no gravitational force, as we are considering no existence of particles. It's just curvature. It's just curvature and an expanding universe. That's it. So there is no effect of gravity in this case. So the relative velocity at any 2 points is basically constant, because there is no curvature at any point and there are no particles as such. So the scale factor at this point, as we can see in equation number 26, it increases linearly with time in an empty universe. Unlike the other kind of universe, as we have seen, it basically increases exponentially, or we can say it accelerates exponentially. So, but in this case of Milne's model of the universe, so you can say that the scale factor increases linearly with time. So at this point in the universe, so we can have a clear look at this graph that can be shown in comparison. So this specific curve of this can be said as the only lambda universe, lambda only universe, or the universe is basically only based on expansion and nothing else. So this is one universe. This will be actually covering it in the later part of the lecture. So this straight line which forms like 40 degrees with the x and y axis, basically the empty universe that we see. So this is the matter only universe, and this is the radiation only universe. So these are the four different components of the universe. So we try all of this. We'll deal it in the later point in the lecture. So I'm just giving you an idea how its dependence with the scale factor is. So this is basically the scale factor, and as time progresses, it's given by the Hubble's law, right? So this is how the expansion of the universe occurs as time progresses. So yeah, the scale factor in an empty expanding universe that we're considering as today, I mean, considering in this case, so it is shown as the dashed line in the graph. So the dashed line in the graph is basically, it shows in the empty universe. So basically, it says about the dependence of the scale factor. So in an empty universe, T naught is directly proportional to 1 by H. That is basically the Hubble's constant. So we can say that it is exactly equal to the Hubble's. So we can say that Hubble's time, I mean the age of the universe is exactly equal to the Hubble's time, right? So in this case, there is nothing to slow or speed up the expansion of the universe. So if a universe has a dense energy density epsilon, which is very small compared to the critical density epsilon c, because we're considering almost no existence of matter or radiation in this specific model of the universe. So the linear scale factor is a good approximation to the true scale factor. It is almost exactly directly proportional to the time. The scale factor directly proportional to the time. So like assume if we are existing in an expanding universe with negligibly small value of density parameter. So we can approximate it as an empty negatively curved universe. So basically what we are trying to say by using the given conditions to explain one model of the universe. So let's try to understand the concept of redshift and proper distance in this model of the universe. So let's say we observe a distant light source, such as a galaxy in which is somewhere, some other place. So we're considering it to be spatially fast. So locally we are saying this is true, and then we observe an object that is, object of observation is pretty far, and then like you have the redshift given that is given by z. So the light which we would observe now at t equal to t naught. So was emitted at an earlier time t equals to t. So t naught here in this case, T naught here is basically the time at which we observe the light that is emitted by the source, and the TE in this case is the time at which the light was emitted from that source. So in an empty expanding universe, from the given the given equation of redshift, we can say that 1 plus z is equals to 1 by a of TE, that is equals to T naught by TE. So it is easy to compute time when the light you observe from the universe of source is emitted, observe from the source is emitted. So T is given by T naught by 1 plus Z. So basically T naught here is basically 1 by H naught, because the age of the universe is the time of observation basically equals to the Hubble's time. So it is H naught 1 by H naught by 1 plus Z. So in any universe that is described by the Robertson-Walker metric, so you can go to the third lecture to understand, to get a more, if you are watching this lecture without watching it, you can refer to the third lecture to understand this Robertson-Walker metric in detail. So the current proper distance from an object is at the origin to a galaxy at a coordinate r, theta, phi is given by the relation in equation number 29, that is dp at a time observation is equals to a of t naught into integration of 0 to r dr. So basically which is r. So why did so in this case you can say I have only r on the right hand side. So because a of t naught is basically the current present moment scale factor, which we always normalize to be 1. So basically my right hand side will only be r. So if the light is emitted by the galaxy at the time TE and is detected by the observer at the time T naught, the null geodesic, as you can see, because we're constant, the null geodesic is followed by the light, satisfies the equation given in equation number 30, that is C times integral of t to t naught dt by a of t is equals to basically equation number 29 can be written in terms of equation number 30. So we get equation number 31, which is basically the combination of equation number 29 and 30. So dp of t naught is equals to c times integral t to t naught dt by a of t. So this equation number 31 holds true in any universe whose geometry is described by a Robertson-Walker metric. So in specific case of an empty expanding universe that we are taking in this case, so a of t is equals to t by t naught is what we have used the relation before also. So you have the proper distance at the present moment is given to be c times t naught integral t to t naught dot dt by t from the relation that we have seen a of t is equals to t by t naught. Since t naught is constant, we can take it outside. So is equals to c t naught into ln of t naught by te. So in terms of redshift, that's what you're trying to find here. So in terms of redshift, you can write the proper distance to be dp of t naught is equals to c by h naught ln of 1 plus z. So the proper distance at the present moment that to a different galaxy or any light source that is present at some distance after, since the universe is also expanding, you can get the proper distance using equation number 33 that is also in the form of the redshift that is being observed from that point. So one note in this thing is that if the if z the redshift is very is a very small value or is very less than like very small value compared to 1. So we can see that there is a linear relation between the proper distance and the redshift, as seen that observation in the Hubble's law. But as z keeps increasing, the proper distance increases exponentially, or it is exponentially proportional to directly proportional to the exponential or the logarithm of z. So it is exponentially related to the proper distance, or you can say redshift. So as the value of the proper distance as the value keeps increasing, we can also say that at distances, that is proper distance greater, very much greater than the Hubble's distance, that is c by h naught, the redshift increases exponentially with distance. So we say that it might like sound not it might not sound we might not be able to grasp it exactly at first, but at first we can say that because we don't consider greater than the Hubble's distance, we say that we cannot like see the object, right? So but one thing to note here is that after the like at the time of emission of the light from the light source, the object would have moved away. So but at the time of observation, it would seem that the object is farther than the Hubble's distance, but at the time of emission, it must have been within the Hubble's distance. So we are able to see the object, even though after time progresses, it may be farther than the Hubble's distance. So I think you get what I'm trying to say here. So when the age of the universe was only 1 by h naught or Hubble's time, so in an empty expanding universe, the proper distance at the time of emission. So the proper distance at the time of emission is given by equation number 34. That is c by h naught times ln of 1 plus z by 1 plus z. So this is the about the curvature only universe, and spatial. Now let's go to the spatially flat universe that we have talked about. So in the spatially flat, we can say by setting k is equal to 0, that is one of the solutions of the Fredman equation. And also we consider only the universe to contain only a single component with a single value that has a single value of equation of state parameter. So we say only one kind of one kind of component is present in the universe, and the k or the curvature is to be 0. It's a flat universe, spatially flat universe. So in a spatially flat a single component universe, the Fredman equation takes a simple form as given by equation number 35. That is a dot square is equals to 8 pi j epsilon naught time divided by 3c square times a power minus 1 plus 3 omega. So to solve this equation, we first make an assumption that the scale factor has the power law of the form a is directly proportional to t to the power q. So we try to because we know the scale factor increases exponentially as time progresses. In this case, in the presence of matter or any component in the universe, so we take a random variable, random value that is t to the power q, which tells us the x, which agrees with the increase in the exponential increase in the scale factor as time progresses. So we get equation number 30. So as we solve for the equation, we get the value of q to be 2 by 3 plus 3 omega. So with the restriction that omega is not equal to -1. That means that we are not the universe is not expanding as such. So this is because of omega is equal to -1. That is equals to exactly the lambda. That is the cosmological constant. So if we are taking it not to be equal to omega, we are neglecting out the cosmological constant. So with proper normalization, the scale factor in a spatially flat single component universe basically is given by equation number 37, that is a of t is equals to t by t naught times 2 by 3 plus 3 omega. So this is the relation that we can come up with using the given t to the power q and q we found out in equation number 36. So we arrive at the equation number 37. So the age of the universe T naught is linked to the present energy density by the relation T naught is equals to 1 by 1 plus omega times c square by 6 pi g epsilon naught to the power 1 by 2 square root of that. So the Hubble's constant for such a universe is h naught, which we have seen before to be a dot by a. So we're considering t should to be equal to t naught at the that's the time that period that we're taking to be equal to 2 by 3 times 1 plus omega times t naught to the power -1. So the age of the universe to in terms of the Hubble's constant to be equal to 2 by 3 times 1 plus omega times h naught to the power -1 or 1 by h naught. So if in a spatially flat universe, we take omega to be greater than 1 by 3. So why we take omega to be greater than 1 by 3. So our value of the denominator increases and greater by -1 by 3. I'm sorry, greater than -1 by 3. So our value of denominator keeps increasing, and we can see that the age of the universe is younger than the Hubble's time. So if omega is less than -1 by 3, so we see that the universe is, I'm sorry, it's the other way around. So if omega is greater than 1 by 3, our value keeps decreasing. So our universe is younger than the Hubble time. So if omega is less than -1 by 3, the universe is older than the Hubble's time from equation number 40, if we substitute in these values for, omega. So as a function of scale factor, the energy density of a component with equation of state parameter omega can be given as epsilon of a is equals to epsilon naught times a to the power -3 into 1 plus omega. So in a spatially flat universe with only a single component, that is what we are considering in this case, the energy density as a function of time that we have seen is basically epsilon naught times t by t naught to the power -2. So that's why we're getting here. And so we can, since from equations 41 and 42, we can make the further substitution in the values of and the present energy density. So epsilon naught is equals to epsilon c comma 0, epsilon c comma 0 to be equal to 3c square by 8 pi g times h naught square. So that we are getting from equation number 38. So we're trying to substitute for the values and get the equation number 43 using the given substitution factors we have here. And your time age of the universe, age of that universe can be given by 2 by 3 into 1 plus omega times 1 by h naught, or h naught to the power -1. So we can all compress all of this equation to be epsilon of t can be given by 1 by 6 pi times 1 plus omega square c square by g times t to the power -2. So this is about the energy density in a spatially flat universe. Excuse me. So okay, so again we are trying to find an expression for the I'm sorry, my throat is a bit dry maybe. So in this case, actually what you can observe in this equation number four, sorry, 1 second. Yeah, right. Okay. So we cannot take the value of 1 by 3 as it would result to 0 in this case. So we can't take the value of 1 by 3 in this. And so yeah, so again, we're considering to find the proper distance as such in this specific type of component of the universe. So if we see a galaxy in this universe or any distant light source with redshift z, we can use the relation 1 plus z is equals to a of t naught by a of te, that is time of observation, scale factor of the time of observation divided by the scale factor of the time of emission of the light. So that is given again by the equation that we have seen before in terms of the scale factor. So we can say t naught by t to the power 2 by 3 plus 3 omega. So we try to compute the value of time of emission, that is t naught by 1 plus z times 1 plus z to the power 3 into 1 plus omega by 2 times h naught into 1 by 1 plus z cubed z to the power 3 into 1 plus omega by 2. So the current proper distance to the galaxy can be given by the equation. So it's quite big, so you can use it for reference here. And in this part, in this section, we cannot use the value of omega to be minus 1 by 3 here. As you can see, we have restricted that part. So if we use here minus 1 by 3, this portion will just result to 0, and then it won't make any sense to have a 0 proper distance as such. So in terms of h naught and z, rather than t naught and t, the current proper distance can be given by equation number 49. So if we see here, the most distant object that we can see for one, which light is emitted at t is equal to 0 and is reaching at some time that is t is equals to t naught, that is an observation time. So this since in this universe you can see that the scale, what do you say, the proper distance that we have seen before was exactly equal to the Hubble's distance, right? So the proper distance in this case can be justified, I mean, can be called as the horizon distance, because you cannot see what is happening in the universe that is far, that is great, whose the distance is greater than the Hubble's distance. So that is what we have established in the previous lectures. So the point, the most distant object that we can see has to be the horizon distance. So in this case, I'm just mentioning the particle horizon distance, as we can. It's based on that. So the maximum distance that we can see is called as the horizon distance in this case. So in a universe governed by Robertson-Walker metric, the current horizon distance in this what is it? The spatially flat universe. So it is equals to c times 0 to t naught times dt by a of t. So in a spatially flat universe, the horizon distance has a finite value if omega is greater than minus 1 by 3. So in such a case, if we find the value of dp t naught in the limit te tends to 0, time of emission tends to 0 is what we are using in this case in equation number 50. So we find the horizon distance to be c by h naught times 2 by 1 plus 3 omega. So in a spatially flat universe dominated by matter, that where omega is equal, the state parameter is 0, or by radiation, that is omega is equal to 1 by 3, an observer can only see a finite portion of the infinite volume of the universe. So that finite portion is what we had established as the horizon distance. So we can only see objects or the light emitted from the objects that are present within or at the distance and not greater than the horizon distance. So as you can also, like, this is basically similar to what we can call it in like a horizon in on Earth also, since we cannot see more than the part of the curve that we can see at one point. So always while viewing the horizon, you're obviously at the center of the the sphere or whatever kind of shape that of whatever shape that you're present on. So the portion of the universe lying within the horizon for a particular observer is referred to as the visible universe for that observer. Yes. So this is again the horizon, based on the horizon distance. So now we are done with the what do you say? The first one was about the energy density component of the universe, only energy density. And then next you have the spatially flat universe, and we also had the curvature only universe. So now let's get into the more more detailed version in terms of matter on the universe. So if we consider only the non-realistic matter to be existing in the universe, which is also expanding in this case, the keynote, a matter only universe which is expanding, as time progresses. So the age of such universe will be t is equals to 2 by 3 times h naught. So this is basically again another solution from the Fredman equation. So and then the horizon distance, what we can say is 3 times ct naught. So if we substitute for t naught here, we have 2 into c by h naught. So c by h naught again we know is the Hubble's distance or the horizon distance. We don't have horizon in this case. So the scale factor as a function of time can be given as t by t naught times 2 by 3. So if we see again, we are trying to calculate the proper distance for this kind of a universe. So if we see a galaxy with redshift z in a flat matter on the universe, the proper distance to such a galaxy at the time of observation is given by this huge equation in equation number 55. So we just, after simplifying this, we just resolve to this part 2c by h naught into 1 minus 1 by root of 1 plus z. So in a flat matter on the universe, the proper distance at the time of observation has a maximum for galaxies with redshift 5 by redshift z is equals to 5 by 4, where the maximum proper distance can be given by the time of emission can be given by 8 by 27 times the c by h naught. So this is the about the redshifts and proper distance in this kind of single matter only universe. So now let's jump into the radiation only universe, as we have covered both non-relativistic. Let's go into the relativistic matter or the radiation only universe. So again, the same case in this in an expanding flat universe containing only radiation. The age of the universe is t naught is equal to 1 by 2 h naught. So the horizon distance is equal to 2 times c t naught, that is c by h naught after we substitute for t naught here. And the scale factor is basically t by t naught times 1 by root 2 or square root of t by t naught. So again, we try to find the proper distance in terms of the redshifts. So redshifts in a flat. So again, we try to make the necessary substitutions after the individual values that we have seen here. So we get the relation in equation number 59, that is c by h naught times 1 minus 1 by 1 plus z. So the proper distance at the time of emission, this is for observation, at proper distance time of observation. So we see the proper distance at the time of emission, that can be given by c by h naught times z by 1 plus z whole square. So the energy density basically in a flat radiation only universe, as you can see, is a ER is equals to E naught, that is energy density at the present moment, times T by T naught to the power minus 1 by 2. Again, this is from the energy density equation, and then you have that is approximately equal to 0.094 times. So we see new terms, that we haven't covered yet in this. So this is basically the Planck's energy and then Planck's length. So this is based on the Planck's Blackbody radiation constant, Blackbody radiation concept. And the Planck's length, the next equation, what you're going to do is based on the Planck's Blackbody radiation concept. So we can also we express, since if first thing that comes to our mind when we think about radiation only and such. So first thing has to be the blackbody radiation, nature of blackbody radiation in that specific universe. So we get into Planck's law of radiation as such. So this is the energy. The EP is nothing but the Planck's energy, and then you have the Planck's length times T by Tp, that is Planck's time. So all of these values, if we see, the Planck's length is basically to the power minus 35, if I'm not wrong. So Planck's length is the measure, is a scale. So it's a measure like if you go beyond Planck's length, or if you go at distances beyond 10 to the power minus 35, if you go into smaller distances, so smaller length, smaller lengths, at that point, the classical laws won't apply. So that's where we get into the classical to quantum transition. So I'll be telling that more in detail. So that's in the early stages of the universe when radiation was stronger. As we know, first it was radiation which was completely strong, and then came the radiation matter equivalence, and then matter started taking over, and then again matter and your cosmological constant had an equivalence point, and then again you have your cosmological constant to be dominating in the current portion of the current time in the universe. So in the early stages of the universe, when radiation was dominant, the energy density is measured in terms of Planck density. So again, EP by LP, that is Planck's energy by Planck's length, to be equal to 3 into 10 of that's this actually we have seen in the previous model, and we've talked about why this is not the kind of measure we have to be expecting to get our values in. So it was almost comparable to 1 over the square of the cosmic time. Cosmic time is nothing but your Hubble's time. So measure of the Planck's time, that is basically approximately 5 into 10 to the power 44 seconds. So if using blackbody radiation, we try to find the temperature of a radiation only universe, and then the energy mean energy of the radiation only universe. So we get these values applying Planck's blackbody radiation concept. So, but what we can see is that as time progresses, I'm sorry, my throat is not coping up with me today. Okay, so as you have seen, the in a radiation only universe, as time approaches to zero, as we can see here, the time approaches to zero, Planck's time. So we get our energy density to be approaching to infinity. So that means at an instant t is equal to zero, the energy density of our own universe, which is approximated as flat radiation only model, so was infinite according to this concept and this analysis that we have for a radiation only universe. So this is very absurd because you cannot have infinite energy density at any point. It's just not mathematically and conceptually right. So why this happens or why are we getting this is basically explaining, or it is basically paving the path for quantum mechanics. As if we try to extrapolate beyond, like up, at a point beyond the Planck's length or beyond the Planck's length, we cannot expect the laws of general. So we see these, all of these what we have derived, it is based on a Fredman equation, and Fredman equation is heavily based on Einstein's general theory of relativity. So we know the general theory of relativity is a classical theory as by nature, right? So if we try to understand the point in the universe at time as time approaches to zero, we are basically trying to go beyond the Planck's length, right? So if we go beyond the Planck's length, again the laws of general relativity or our classical laws are not applicable. So that's why we're getting this absurd result as, you know, the energy density to be infinity. So this doesn't make any sense. So yeah, so so then we have the concept of, you know, the quant radius. So all of this is basically what I've said in the, like in the summary. We have used integration all over. So just assuming that the all the energy is both continuous at all points and at all points and all stages of the transmission of energy from one point to another. So then if this result can also be, you know, made better by assuming the energy to be quantized and not, you know, continuous throughout. So that is one of the assumptions that you have to make. I mean, that is one of the concept that you have to apply if we want to you know, get a proper understanding of a radiation only universe. So that is about the radiation only universe. And so we have now the lambda only universe. This is just for the closure, as we have considered every case of equation of state parameter, that is zero. We have 1 by 3 for radiation, and then you have minus 1 by 3 energy density. Then so you have the omega equation of state parameter to be -1. So this is basically nothing but the universe that is completely dominated by the cosmological constant. Like there is nothing but the cosmological constant as such. So for a flat lambda dominated universe, we have the Fredman solution. That is A dot square is equal to 8 pi g epsilon lambda by 3c square times c square. So where epsilon lambda is constant with time, as we know, because the expand, or what do you say, the as you have seen in the previous models, like most of this what I'm saying is basically a kind of a continuation from my previous lecture. So please people, if you are trying to, if you are viewing this video first, you can also refer to the previous one. So it is, since this is constant with time, so our equation number 64 can also be written in short form. I mean, wherein you can just just compress this whole term, because all of these are constants. Compress the whole term to be a constant, Hubble's constant, and you have a dot is equals to h naught times a. So h naught is equals to 8 pi is root of 1 by root of 8 pi g epsilon lambda by 3c square. So again, you have h naught is equals to a dot by a. That is again Hubble's law. So solution for equation 65 in an expanding universe is, after we try to solve this differential equation, so we have a of t is equals to e power h naught of t minus t naught. So in a spatially flat universe with nothing but the cosmological constant is exponentially expanding, as you can see in equation number 67. So basically, from what we have seen, I think in my second lecture, we have seen what is called as the steady state universe. So steady state universe assumes that the universe is expanding, but the density of matter and the matter and energy density to be constant. This was one of the wishes of Einstein to try to support the theory of steady state, and he failed actually by just pulling up a trick move all by himself, and by just substituting the value of lambda in his field equation and expecting it to compensate for the missing, I mean, the increase in the energy density or decrease in the energy density based on the value of lambda in the given equation. But that also proved to be otherwise after people started to understand the significance of lambda in the Einstein's field equations. So in this case, the cosmological constant lambda is since we don't have matter in the specific universe, so, or energy in the specific universe, so we say that the cosmological constant is provided by the vacuum energy. So vacuum energy, as you have seen also in the previous lecture, so we can say that the density also remains constant, because in vacuum you have virtual particles that are always produced in pairs of a part which is a particle and an antiparticle. So these both, they, as soon as they come into existence, again after a certain period of time, they just annihilate with each other as their opposites. So then again they go back to being what if it is going back to being vacuum. So this is basically, it doesn't affect the actual density of the universe that you're in, and because it's in it's the concept of vacuum energy and virtual particles. So this is the kind nature if we want to try to understand the cosmological constant in the steady state universe. So in a flat universe containing nothing but a cosmological constant is infinitely old, because you just have the expansion of the universe and nothing else. And so so it has an infinite horizon that makes sense, right? It has an infinite horizon distance. So if in a flat lambda only universe we see a light source which has a redshift z, so the proper distance to the light source we'll observe is c times the integral t to t naught e power h naught of t naught minus t minus 1. So basically sorry. So what we have seen in this AT, right? So we have, since, so if we apply the AT minus 1, that is basically the relation for the redshift in terms of scale factor. So we have c by h naught times z. So the proper distance at the time light was emitted, basically we can simplify the whole thing. So it will be at the time light was emitted. This is for at the time it was observed. So for the time it was emitted, you have c by h naught times z by 1 plus e. So this is the one factor you have to take care, because the scale factor would have increased by the time you try to observe time of emission and at the time of observation. So the exponential, as you can see, the universe, this model of the universe is exponentially growing. So such as the flat lambda dominated model which we are using in use before. I mean, using it right now. So in a universe for which the proper distance at the time of observation is linearly proportional for z for all values of z. So as you have seen in a spatially flat universe, if I'm not wrong, so in that you see that at different values of the redshift, you'll also have different rates of expansion. So if my value of redshift is very less than one, so we can say that the proper distance is basically linear with the scale factor, or the redshift is basically linear with the expansion of the universe. But as the value of redshift keeps increasing at larger distances, again you'll have it'll exponentially increase. But in this specific case of the universe, we just have just a linearity with the scale factor. So just the proper distance is basically directly is linearly proportional to the redshift. So we see that at the time, so the observer see them as they were just before they reach the proper distance of c by h naught. Again, this is the Hubble's distance, so we can not see more further than this. And yeah. And so once the source of light source is more than the Hubble distance from the observer, the recessional velocity is greater than the speed of light. As we are saying, like as the speed, I mean, the universe is also expanding linearly. And then also if the distance is greater than the Hubble's distance, the light will take infinite years or like very long time to, reach to our eyes. So we can practically not see them, throughout our many lifetimes, and it takes such a long time to reach us. Basically, you can consider it to be infinite. So the the objects that are present within the Hubble's distance in this specific universe are causally connected with us. So the light or the objects that are present in the within the Hubble's distance basically can affect us, as we can see the act of observation. So we can try to see the objects, and we can try to comprehend the objects. But at distances greater than the Hubble's distance, we can say they are causally disconnected from us, because no matter what happens there, it's not going to affect us. No matter what even if the particular galaxy, try to, or a specific star that is present outside the Hubble system, it explodes and it even forms a black hole. It doesn't, bother us anymore, because we won't be. It is way far than the Hubble's distance, and it is causally disconnected from us. So, and we cannot, expect to observe the specific object or what happens to the object that is greater than the Hubble's distance. So basically, this is basically what I'll be covering in this specific lecture. So one specific thought, or one specific interesting thought experiment that we can try to do after we have seen after we have seen the single component universe, is that, say, if is it possible to have universe which stop expanding, or and then like start to collapse, like how we saw while deriving the Fredman equations. We saw the value as the value of u 10 is less than, if it's less than the 0, so you'll have you, you'll have the universe to be constantly, it'll start to slow down the expansion, and then at one point it just like collapses, right? So yes, the answer is basically yes. We can have such universes. That universes can exist only if we like combine two or more components of the universe to get a multiple component universe. So basically, you can have like radiation matter universe, and then you have cosmological constant matter universe, cosmological constant and radiation universe. You can have various, mixtures of these components in a single universe, which will try to which will give you various results for each of the given observable that we have seen in this part. So that is one of the interesting interesting point that we can take from this and try to build upon that, and reach to a higher understanding of what our basic universe can actually be, and why our universe is behaving, why our universe is as the way it is. So this is where I'd like to end my lecture. So thank you for your patience, and thank you for attending this lecture. Yes.